So good morning. This is the last part of our module number 4. So we are going to discuss about linear pipeline processors and non-linear pipeline processors. After that, we'll have a short insight into what is superscalar pipeline processors, or what we say super pipeline processors. So let's start with linear pipeline processors. So when you talk about linear pipeline processors, as the name says, it is going to have a linear fashion in its execution as well as in its ordering. So such kind of a pipeline is called a linear pipeline processor. Now, what happens when you talk about a linear pipeline processor? So here you have so many stages, just like any other pipeline. You have so many stages, and these stages are cascaded to one another, which means the input of another stage will be the output of its previous stage. So they are arranged in a linear fashion. And they are put together to form the form the stages of the pipeline. So this kind of a pipeline processor is applied for instruction execution, then computation, and also for memory access operations. So you can use it for instruction execution. You can use it for some arithmetic computations and also for some memory access operations. So a linear pipeline processor, just like any normal processor, it will be the pipeline is going to comprise of k stages. So you call it as a k stage pipeline. So the external inputs are fed into the pipeline at the stage number 1, and the processed results are passed from stage Si to stage Si plus 1. So as I said before, the output of the previous stage will be taken as the input to the next stage. Okay, so the processed results is available with the stage Si, and that will be given to the stage Si plus 1 as its input. And when you talk about a k stage pipeline, the final result will always be available with the last stage of the pipeline, which is stage number k. Okay, so S1 is receiving the external inputs. All other stages are receiving the inputs from its previous stages, and the final result of the exercise, the final result of the computation is going to be emerged from the last stage. So this is about the linear pipeline processor. It has got two models. The first model is an asynchronous model, which is most widely in use, and the second one is a synchronous model, which is used in the case of some workstations and all. So about the linear pipeline processor, about the asynchronous model, here if you want to transfer data from one stage Si to its adjacent stage Si plus 1, that occurs based on some request response signals, or what we say handshaking. Okay, so the data flow between adjacent stages in an asynchronous pipeline will be controlled not by a global clock but by a handshaking protocol, and you can see it is input. The input is the channel by which the data transfers through the pipeline. Then what you see, ready and acknowledge. These are the signals that is used for the handshaking protocol to work on. So these ready acknowledgement lines, they actually help to uh, successfully transfer the data or between the successive stages of the pipeline. So when a stage is thinking to pass the data to its adjacent stage, or thinking to pass the output of its output to the next stage, first it has to request the receiving stage to know whether it is ready to accept the data that is being incoming to it. So if it is ready to accept, it will send back an acknowledgement signal, and after that the original data will be taken to the channel and it will be passed to the corresponding stage of the pipeline. So this is how the asynchronous model of linear pipeline processor actually works. It is even if it is in the case of a non-linear pipeline, it is also having the same thing. It is also having these asynchronous and synchronous models. So when the stage Si is ready to transmit, it sends a ready signal to Si plus 1. When the Si plus 1 is ready to receive, it will send back the acknowledgement signal. So this is actually useful in designing the communication channels in the message passing multicomputer, where we actually practice pipelined wormhole routing. Then you cannot guarantee about the throughput when you are talking about an asynchronous model, because it varies from time to time, it varies from stages to stages. Different amounts of delay may be experienced in different stages because of the handshaking protocol. Maybe the stage should be ready to receive it, it is late in sending the acknowledgement signal. So all these actually can make up uh, uh, make a restriction in the performance of the system. So that is why it is so told that the throughput rates may be variable in the case of a asynchronous model of linear pipeline processor. Moving on to synchronous model. So as you can see, in the case of a synchronous model, there is someone called a latch that is being associated with each of the successive stages of the pipeline. So each individual stage, right from S1 to SK, they are having its own latches. And these latches are connected to the global clock, which help them to alert the stages to be active at the same time. Okay, so as you can see, each latch is given a message, or each latch is given a control signal whenever you can see a rise in the clock cycle. So whenever there is a rise in the clock cycle, S1 will transfer its content to S2, S2 will transfer its content to S3, and so on. So this is how a synchronous model works. It requires a global clock and successive placement of latches along all the stages of the pipeline. So this is about the synchronous model. So let's see more of them. So there are clogged latches, which is made of the master slave flip-flops. I think you have already learned all this in your paper on logic system design or electronic devices and circuits. So these kind of latches can isolate the inputs from outputs and are used to interface between the stages. So before you actually see the stage, there will be a corresponding latch which helps to activate that particular stage. Upon the arrival of a clock pulse, all latches transfer data to the next stage simultaneously. That is why I said whenever there you can see a clock cycle rise, whenever you can see a rise in the clock cycle or the rise in the clock signal, you can be assured that all the latches initiate a transfer of data from the current stage to the next stage. Okay, and all of them happens at the same time, and that is why this is called a synchronous model. It is designed to have approximately equal delays in all stages, else it will be difficult to achieve the performance level. So these delays determine the clock period and thus the speed of the pipeline. The utilization pattern of successive stages in a synchronous pipeline is specified by something called a reservation table. You can even use the reservation table in the case of a asynchronous method also, but it is most widely used in the case of synchronous model. For a linear pipeline, the utilization follows diagonal streamline pattern. So I'll show you an example on what is the reservation table and what do you mean by a diagonal streamline pattern. Okay, then yeah, the table or the reservation table, it's a space-time diagram depicting the precedence relationship between the pipeline stages. Okay, so for a k stage pipeline, you will require k clock cycles for the data flow from the input to the output. So you can, when you draw the table, it will be a case k by k table, and obviously you can see that in the case of a synchronous linear pipeline, you can see that this will be having a diagonal pattern, and that is what being told in the previous bullet point. So this is an example of a linear stage pipeline where you have got 4 stages, and this is the clock cycle. So when you say a 4-stage linear pipeline, it is evident that if an input has to reach the output, you require 4 clock cycles. Okay, for an input to reach the output, you require 4 clock cycles, or the first output comes in the 4th clock cycle. So on one side, on in all the rows you see the stages, and in all the columns you see the time. Okay, so this is in the case of the synchronous model. As we said, each of the stages having its equal delay, each of the stages having equal delay. So no one is having any extended delay or lesser delay, not like that. All of them are having equal delay. So if that is the case, then you can see that in the first clock cycle, stage 1 will be in use. In the second clock cycle, stage 2 will be in use. In the third clock cycle, stage 3 will be used. And in the final clock cycle, which is the cycle where you receive the output, your fourth clock cycle, that stage will be the final stage of the pipeline. So this is in the case of a 4-stage pipeline. So in the case of a 4-stage pipeline, you require 4 stages and the correspondingly the number of clock cycles, and you draw the reservation table. So this is the case of a 4-stage pipeline. So the successive tasks or operations are initiated one per cycle to enter the pipeline. Once the pipeline is filled up, one result emerges from the pipeline for each additional cycle. This throughput is sustained only if the successive tasks are independent of each other. So you have to ensure that the instructions are parallelly executable. The instructions are not dependent. You have to apply all the Bernstein's conditions. You have to check whether there is a dependency. If you have a dependency, you have to resolve the dependency and then ensure that the instructions are not dependent on each other. So if you have a dependency, you will have to stall the pipeline successively. That will be reflected in the reservation table also. So this is in the case of reservation table synchronous model of linear pipeline processor. Moving further, we have to know how you can analyze the speed up, the efficiency, the throughput, and the optimal number of stages required for a linear pipeline processor. So from the next slide, we will see that. So yeah. So when you talk about the clocking and timing control, we have to talk about the clock cycle, we have to talk about the throughput. So just like before, here tau is going to represent the clock cycle, tau I is going to represent the delay of the circuitry or delay of the pipeline, the installed pipeline at a stage Si. So when you say tau I, it is going to talk about the time delay of the circuitry at the stage Si. Now we have to see what is the maximum stage delay. So maximum stage delay will be the maximum of all the delays of the stages of the pipeline. So you will have to identify what is the individual stage delays, take them, find the maximum value, that will be the maximum stage delay. And you will have to add something else, which is D, and D is the pulse width. Okay. So you can say the tau, which is equal to the tau m, which is tau m stands for the maximum stage delay plus D. So D is the it can be taken as the delay, it can be taken as the latency or the latch delay also. In the case of synchronous, D stands for the latch delay. In the case of asynchronous, it is the delay that occurs while you are transferring data from an individual stage to its adjacent stage. So at the rising edge of the clock pulse, this is in the case of synchronous model. So at the rising edge of the clock pulse, the data is latched to the master flip-flops of each latch register. Then the clock pulse is taken to have a width equal to D. Then when you see in general, you can be sure that this D value, which is the width of the clock pulse, it is actually too less compared to the maximum stage delay. So you can even neglect that particular value, which is D. So when you talk about when you say that the clock cycle is equal to maximum stage delay plus D, where D is the width of the clock cycle, you can be sure that the maximum stage delay is too huge compared to that of D, which is the width of the clock cycle. So you can even ignore the effect of the width of the clock cycle while you are computing the clocking and timing control. So when you talk about the pipeline frequency, as we have discussed before in module 1 and module 2, the pipeline frequency F is equal to 1 divided by tau, when you talk about the frequency, here also the pipeline frequency is equal to 1 divided by tau, where tau is the clock cycle of the pipeline. Now, the F represents the maximum throughput. So, we had initially we had some other equations for finding the throughput, but here in the case of a pipeline, this F factor is going to be the throughput of the pipeline. So, F represents the maximum throughput of the pipeline. Actual throughput may be lesser than this computed value of F, that is based on the initiation rate. So, there is something called clock skewing. Clock skewing is that actually we expect all the clock pulses to arrive at all stages at the same time. That is what we have discussed in the case of synchronous model, right? So you have a latch, and the latch is going to initiate the transmission upon the rise of each clock pulse. But when you take it into reality, you can see that it is not the same as expected. Okay, so even if we expect the clock pulses to arrive at all stages at the same time, due to a problem called clock skewing, the same clock pulse may be arriving at successive stages at different timings. Okay, and that difference in the time is called an offset, a time offset, and we denote it using the letter S. So T max is the time delay of the longest path within a stage, and T minimum is the time delay of the shortest logic path within a stage. Remember, it's not within the pipeline, it is within the stage. Okay, so T max is the longest logic delay, T minimum is the shortest logic delay. Now, when you say about clock skewing or time offset, in the case of an ideal pipeline, you will never experience an offset, you will never experience a difference, and you can say that in the case of an ideal pipeline, S is equal to 0. If S is equal to 0, then the maximum longest logic path is equal to the maximum stage delay, and you can say T max is equal to tau m. Similarly, T minimum, the minimum or shortest logic delay that can occur from a stage is the delay as the length of the clock cycle. So that is equal to B. So T max is equal to T max is equal to tau max, where tau max is the maximum stage delay of the pipeline. Similarly, T minimum is equal to D, where D is the width of the clock cycle. So if you don't have a clock skewing problem, which means you don't have a difference, you don't have an offset, S is equal to 0. In that case, tau is equal to tau m plus D. Whereas if you have clock skewing, you will have to consider that offset, and that will be written as D plus, it will not be tau m, it will be T max plus S. Okay, T max plus S less than or equal to tau less than or equal to tau m plus T minimum minus S. So then if you have the clock skewing problem, the tau will be having a range from D plus T max plus S to tau m plus T minimum minus S. So this will be the range of the value of tau. Okay, this is in the case where you actually have an offset. If you don't have an offset, then tau is equal to tau m plus D. Moving further, you have to talk about speed up, efficiency and throughput. So, when you talk about a linear pipeline of k stages, you are sure that it can process n tasks. Okay, it can process n tasks in a total clock cycle. Total number of clock cycles taken as k, which is the number of clock cycles or number of stages of the pipeline, plus n minus 1, because once the first instruction reaches k, once the first instruction is producing its output, the second from each clock cycle to come after that kth clock cycle, you will expect to receive one output. So that is in the case of linear pipelines of k stages. So the total number of clock cycles required for the final output to emerge is actually k plus n minus 1, where n is the total number of instructions. Okay, or total number of tasks. So the total time required by a pipeline is equal to tk is equal to k plus n minus 1 into tau, where tau is the clock cycle time. Okay. So when you talk about the speed up, okay, so when you talk about the speed up, it is measured using sk. So sk is equal to T1 divided by Tk, where T1 is the amount of time it takes to execute n tasks, the same n task in a non-pipelined processor. Okay, so T1 is the total time taken for executing the same n task in a sequential manner in a non-pipelined processor, whereas Tk is the total time taken to execute the same end task in a pipelined processor. So speed up achieved is equal to the total time taken by a non-pipelined processor divided by the total time taken by a pipelined processor. Okay, so the total time taken by a non-pipelined processor is equal to n into k into tau divided by the time taken by a pipelined processor is equal to k plus n minus 1 into tau, which you can expand and write it as k tau plus n minus 1 tau. So applying everything, speed up is having an expression which is n into k divided by k plus n minus 1. N into k divided by k plus n minus 1. That is the expression for calculating the speed up of a linear pipeline processor. So this is the total time taken and this one is the speed up achieved. Moving on, here we'll have to talk about the optimal number of stages that you can have in a pipeline. So when you talk about the general pipelines, it is seen that the number of stages ranges from 2 to 15, which means k is having a value between 2 and 15. And when you talk about the optimal number of stages, how can say the optimal number of stages? Okay, when you say my pipeline is having the optimal number of stages, you have to make sure that you can produce or the pipeline is able to produce maximum value for performance cost ratio. So performance divided by cost, that ratio should be maximized, which means maximum performance, minimum cost. If the number of stages could achieve this particular thing, which is the maximum performance cost ratio, then you can say that it is the optimal value for number of stages of the pipeline which is being under the design. Okay, so when you say T is the total time for execution in the case of a non-pipeline sequential program, when you take a k stage pipeline to execute the same program, you expect a clock period of P is equal to T divided by K plus D, where D is the latch delay. Okay, so P is equal to T by K plus D, that is the expression for clock period. And when you say about T is the total time taken to execute a non-pipeline sequential program in a non-pipeline processor. And P is the clock period required to execute the same program in a K stage pipeline. Okay, expecting a equal flow delay of T. Then the maximum throughput that you can achieve using this pipeline, F is equal to 1 divided by P, which is 1 divided by P stands for P can be expanded as T by K plus D. So F is equal to 1 divided by T by K plus D. Now we have to talk about, so that is the throughput or performance of the pipeline. Now we have to talk about the cost incurred in the pipeline. So when you say about the total cost of the pipeline, it is an expression which is C plus KH, where C is the cost of all the logic stages that is being involved in creating the pipeline. Okay, so it is the total cost incurred while you are purchasing or you are implementing all the logic stages, that is C, plus you have K stages, so K into the cost of each latch. Okay, so when you talk about the total cost, it is equal to C plus K into H, because you have K stages, so you will require K latches. So each latch is making a cost of H, so K into H gets you the total cost for the latches. and the C is the total cost for all the logic stages. So the total cost is equal to C plus KH. Now talking about the optimal number of stages, you will have to find out what is the pipeline performance cost ratio, or what we call PCR. So when you talk about PCR, as the name says, it is performance divided by cost. Okay, so what is performance? Performance is F. So F divided by cost is C plus KH. You get PCR. So you can expand F and you get the expression as 1 divided by T plus K, 1 divided by T divided by K plus D into C plus KH. So using this expression, you can plot the PCR curve, and the peak value that you see in the curve stands for the optimal number of stages. Okay. So you can find out that optimal value KO as root of T into C divided by D into H. T into C divided by D into H. That stands for the optimal number of stages if you are given with a pipeline. So while you are designing a pipeline, all these values of speed up, throughput, the delay, then also the optimal number of stages will come into a practice, will come into use. You will have to consider all these while you are going to decide on what should be the number of stages of your pipeline, because all the time the designers are ensuring that the number of stages chosen is the optimal. Okay, so that is about the optimal number of stages. Moving further, this is the equation for efficiency. So talking about the efficiency of a pipeline is equal to the speed up achieved divided by the number of stages. So speed up achieved is Sk, and that was equal to n into T divided by K plus n minus 1. So that is there. So divided n into K divided by K plus n minus 1. Now when you divide it with K, you have the expression for efficiency as n divided by K plus n minus 1. Now when the efficiency will always be having a value between 0 and 1. So when the efficiency approaches 1, when n tends to infinity, and the lower bound on Ek is 1 divided by K, where n is equal to 1. Now you talk about the pipeline throughput. The pipeline throughput is defined as the number of tasks performed per unit time. So what is the number of tasks? It is n. Unit time, you have to talk about the unit time, that is K plus n minus 1 into 2. So when you talk about the throughput of the pipeline, this linear pipeline or any pipeline, you have the expression for throughput as nf divided by K plus n minus 1, because 1 by tau is equal to f. So you just replace 1 by tau with f, and you can write it as nf divided by K plus n minus 1. So these are various equations that you can use while you are going to design a pipeline. Okay, so when you are going to design a pipeline, you have to know what are the logic stages involved, what is the cost involved, and how you can decide on the optimal number of stages. Okay, so once you decide on the optimal number of stages, you can achieve the correct value for efficiency, because optimal number of stages will always maximize the performance and minimize the cost. And so apparently you can achieve a better throughput in the pipeline also. Now that's all about linear pipeline processor. So about the non-linear pipeline processor, I'll be explaining in my next lecture. So you can make use of these equations. You can go refer to your standard reference book. You can see questions that are being asked from this particular portion. You can try to resolve them and also understand the concept very well. So thank you. Have a great day.